Hello and welcome back to another Math 104 lecture. So in the last lecture, we had just started getting on to the topic of trigonometry. We looked at how we value angles. So that's basically where we left off. We were talking about angles. So we discussed degrees, radians, and the such. And if you're keeping up in the textbook, that was chapter 5.1. And now what we're moving on to is chapter or section 5.2, where we are going to start examining right triangle trigonometry. And this is where we're going to first introduce the concept of some trigonometric functions. Now, I'm sure you've heard of these before, but whether or not you've heard of them and you actually understand them, or you've just seen them in passing, we're going to write them all out here today. So let's just first start with drawing a triangle, and it has to be a right triangle because, again, all of this trigonometry that I'm about to show is based off of right triangles. So let's start with a right triangle. Let's say we have a right angle here, and we'll call this triangle ABC. So we have a right angle at angle C. And what I'm going to call the legs here are just lowercase of the opposite angles that we have. So opposite of angle A, I'm going to have side A. Opposite of angle B, I'm going to have side B. And opposite of angle C, I'm going to have side C. So nothing too out of the ordinary. Again, this is just a right triangle, and now it's fully labeled. Okay? So to get started, let's list out the trigonometric functions that we're going to be using. So first off, we have sine, cosine, and tangent. And just to finish writing them out, these are the abbreviations for them when you write them in your equations or in anything else in math. We generally abbreviate them, but again, these are so sine, cosine, and then tangent. But I'm just going to leave them as abbreviations just, for the sake of it. So we have sine, cosine, and tangent. And when we're talking about sine, cosine, and tangent, again, you have to consider these are like functions. And with a function, remember every function has some kind of input, right? When we were talking about f of x, remember that the input to your function f was the x, right? So when we're talking about sine, cosine, and tangent, and the three others that we're going to get to in just a second here, what they're taking in is the angle that you're referencing. So we generally abbreviate, or we generally put theta here because, again, we're talking about angles. Now, we can also replace theta with specific angles. So if we're referencing our right triangle that we just created here, notice again we have angle A, which I'm going to circle in red. So angle A. We could, if we wanted to find the sine of A, what we would write is we would write sine of A, and that's it. And that's, just as easy as it is. You just replace theta with whatever your specific angle is. But in general, because we call our angles theta or phi, as we detailed in the last lecture, that's generally the Greek letters that we use. But it's not uncommon to see, actual letters here that correlate to the triangle. Okay, so we have sine of theta, cosine of theta, and tangent of theta. So we have to figure out what these are. Now, there's a mnemonic device that, again, some of you have probably heard before, that we're going to go over. And the mnemonic device is called SOHCAHTOA. It's super easy to, flows off the tongue, super easy to remember, SOHCAHTOA. And to write it out, SOHCAHTOA. SOHCAHTOA. What does this stand for? Well, you're supposed to break it up into three parts, and we'll figure out what it all means. So breaking it up into three parts, we now see we have the so, the ka, and the toa, right? All right, so let's break down what each of them mean. The first letter of each of these parts refer to one of your trigonometric functions that we're discussing here. So the S, as you can imagine, refers to sine. So this says, okay, sine, and the O means opposite. Well, what are we talking about when we say opposite? If we're talking about, let's just take angle A, for example, and say I wanted to find the sine of angle A. So let's do this. Sine of angle A. What is opposite of angle A? Well, opposite of angle A, we're talking about the side that is opposite of angle A. So that's going to be this guy. The side that's opposite of angle A is the side lowercase a, right? So again, to detail this, if we're discussing opposite, we're talking about the side that is directly opposite of the angle in question. And then H is always going to stand for hypotenuse. Okay, I'm going to abbreviate it as just HYP, but H is always the hypotenuse. Regardless where your angle is, your H is always hypotenuse. Now remember, what is the hypotenuse of a right triangle? Hypotenuse of a right triangle is the longest side of a right triangle, and it is also the side that is always opposite of the right angle. So in this case, the side that's opposite of the right angle and the longest side is side C. So if I wanted to find the sine of A, for example, then the sine of A is going to be opposite over hypotenuse, which I'm going to label as this, O over H. And what is that in terms of the letters that we have? Well, again, opposite of angle A is going to be the side, and hypotenuse is going to be C here. So sine of A is really just A over C. And it's that easy. That's all it comes down to. And let's go ahead and based off of what we, based off of this picture that we have, let's go ahead and figure out everything else again, just with reference to angle A. So let's go ahead and figure out cosine of A and also tangent of A. So cosine of A, well, let's refer back to SOHCAHTOA. What does SOHCAHTOA say? For SOHCAHTOA, we have that middle piece, ka, right? Again, the first letter is indicative of one of your trigonometric functions. So we're now talking about cosine, right? All right. So for here, we're talking about cosine. The letter after C, that A, stands for adjacent. A will always be adjacent. O is always opposite. H is always hypotenuse. So we have adjacent. What is the side that is adjacent to your angle A? Well, adjacent basically means next to, right? And so you could think, well, technically there's two sides that are next to angle A. There's this one and there's this one. But remember that this is your hypotenuse, right? So that's immediately ruled out. We're not talking about that side. We're talking about the side that's adjacent to angle A that is not the hypotenuse, right? So that's going to be the B. Okay. So sure, when we're writing this, we know again, SOHCAHTOA, this says we're going to have adjacent over hypotenuse. And so adjacent over hypotenuse, well, and let me just abbreviate, I'll call this adjacent, just so we don't get confused with A and actual side of A. So again, this means we're going to have the side that is adjacent to angle A, which is B, over your hypotenuse, which is C. So that means B over C. Okay, great. Let's keep moving. We have now tangent of A. Okay, so tangent of A, well, the last piece of SOHCAHTOA is, again, T stands for tan, and O is always opposite, like we just talked about. A is always adjacent, again, just like we discussed. So for tangent of an angle, it's always the opposite side over the adjacent side. So we look at our angle A, and again, this is going to be opposite over adjacent. Okay, so opposite over adjacent, the side that is opposite of angle A is side A, and the side that is adjacent to angle A is side B. So we have tan of A is just A over B. Okay, so again, the mnemonic device is really helpful, SOHCAHTOA. If you could remember that, great. If you can just remember that, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, even better. The reason that's even better is because when we get to the next three trigonometric functions, which are essentially reciprocals of these, you can basically just flip them on their heads, right? You can just take the fraction that you have and just, flip it upside down and you're good to go. But if you remember the mnemonic device, at the very least, you are starting with something and then you can build off of that. Okay? So we just figured out, based off of our picture, what sine of A, cosine of A, and tangent of A are, right? Okay, let's do one better. Let's keep going. What I want to do now is I want to discuss the next three trigonometric functions. So the next three that we're going to discuss are cosecant, secant, and cotangent. So to write these out one more time, so if we have, this is cosecant, which we abbreviate as CSC, so CSC. There is secant, which we just abbreviate as SEC. And finally, there is cotangent, which we just abbreviate as COT. Okay, so again, cosecant, secant, cotangent. All right, and now again, remember, because these are functions, they need an input, right? So for the purpose of our picture and just for the purpose of, filling things out, making things match, we're just going to keep referencing angle A. So I'm just going to keep saying, okay, cosecant of angle A, secant of angle A, and cotangent of angle A. So to figure out what these are effectively just reciprocals of the first three that we learned. Okay, now please make sure you're getting the correlation correct. Cotangent and tangent correlate really easily, right? You can probably figure out that cotangent is just going to be the reciprocal of tangent. But a lot of students confuse the reciprocals of sine and cosine. They think that, okay, well, because sine starts with an S, they think that, oh, the reciprocal of sine should be secant. This is incorrect, okay? Notice how I wrote this diagram, right? I wrote sine with the cosecant. I wrote cosine with the secant and tangent with the cotangent, right? Okay, sine will always have its mirrored reciprocal partner being cosecant, okay? So sine, cosecant. The way you can think about it and the way that we're going to detail this is, again, I keep using the word reciprocal, right? Reciprocal essentially means when we're talking about fractions, it's, the same numbers, but just flipped upside down, right? If we're talking about the fraction 2/3, the reciprocal of 2/3 is 3/2. It's just taking your fraction and flipping it upside down. So if we're talking about cosecant and sine, and I'm saying that cosecant is the reciprocal of sine, well, then that means that we're taking our fraction and flipping it upside down. If you're trying to correlate the two, if you're trying to think of, okay, how am I going to remember this in my head? How do I remember that cosecant and secant are pairs and sine and cosecant are pairs? How do I remember this in my head? Well, you can think about it this way. If you're flipping the fraction upside down, you should also flip the letters in your head, right? So we're starting with the letter S, right? S for sine, and then we get to C. And then for cosine, we're starting with a C, but we're getting an S. So just try to find some way that's what's always helped me. If you didn't follow that, if that only confused you more, I'm sorry. Just try to find some way to memorize the partnership between these, because again, a very common mistake is thinking that cosine goes to cosecant and that sine goes to secant, and that's incorrect. That's going to mess you up down the line. So please try to get this hammered in your head now. Sine is the reciprocal of cosecant, and then vice versa. Cosecant is the reciprocal of sine. Cosine is the reciprocal of secant, and secant then is the reciprocal of cosine. Okay, so, and then obviously the easy one, tangent and cotangents, reciprocals of each other, right? Okay, so if we're trying to figure out the values of this, and again, we're referring back to our diagram here, and we're talking about angle A, again, remember what I just said. Cosecant is supposed to be the reciprocal of sine, which means we're taking our fraction and essentially flipping it. So instead of it being opposite over hypotenuse, this is hypotenuse over opposite, which basically says, okay, well, our hypotenuse is still little c, our opposite is still a, it's just flipping the fraction on its head. So instead of it being a over c, it is now c over a, okay? For secant, same idea, right? Instead of it being adjacent over hypotenuse, it's now hypotenuse over adjacent, which says, okay, so instead of it being side b over side c, now it's going to be c over b. And last but not least, for cotangent, again, same idea. Instead of it being opposite over adjacent, it's now supposed to be adjacent over opposite. And this tells me that instead of it being a over b, it should be b over a. Okay? Now, there's one last thing that we have to discuss as far as tangent is concerned, and then also as far as cotangent is concerned, because they have this weird partnership as far as them being reciprocals. Tangent also has another definition. So we define tangent as being opposite over adjacent, right? There's another definition of tangent as well. We can actually define tangent of A, or of any angle. Well, we can just replace this with theta. Tangent is actually going to be equivalent to sine of your angle over cosine of your angle. How does this make sense? Where are we getting this from? Well, if you think about it, what is sine and what is cosine? Let's look at our examples here, because again, we're deriving, we're using the angle A, right, from our picture here. So let's try to put this together. If we want to try to define tangent by this new definition of sine over cosine, well, let's think about what we actually have. Sine of A is opposite over hypotenuse, right? So if I'm, really thinking about it, tangent of A should be sine of A over cosine of A, right? And again, we just discussed that sine of A is opposite over hypotenuse, right? So this is the same thing as what we just figured out. It should be side A over side C, right? So that should be my top, A over C. And this is all over what cosine of A should be, right? Cosine of A is side B over C, like we just figured out, right? That's adjacent over hypotenuse. So this is B over C. And now we have this complex fraction, right? We have A over C divided by B over C. Well, we know how to solve this, right? Even if you, don't fully understand how to just get rid of this, because, you might recognize, to make things faster, that you have a common denominator of C and C, so you can just essentially get rid of that. But if you don't see that immediately, that's okay. Use keep, change, flip, right? What does this become? This is the same thing as A over C times C over B, and then the C's cancel out, right? And we're just left with and we are just left with A over B, which is exactly what we got when we defined it by opposite over adjacent, right? Notice how we still ended up with A over B. So it doesn't matter how you're defining tangent, whether you're considering it as opposite over adjacent, or whether you're considering it by this new definition, sine over cosine, you still end up with the same values regardless. Okay, and now because cotangent is the reciprocal of tangent, well, now you can probably infer what's going to happen, right? Cotangent of theta of some angle, right? Doesn't matter what the angle is, should just be the reciprocal of tangent. So in theory, it should just be cosine of theta over sine of theta. And that's all there is to it, okay? And now, again, because we were talking about cosecant and secant being reciprocals, you don't necessarily just have to think about it as specific sides and taking that fraction and flipping it, right? We can actually define sine as 1 over cosecant. And I know that I'm foregoing the thetas here, but just bear with me. It's, just to speed things up, right? So the reason, and this is an equivalent statement to saying cosecant is equal to 1 over sine, right? Where are we getting this from? Again, if we're talking about reciprocals, well, sine is the same thing as sine over 1, right? And so if we're talking about reciprocals, cosecant should be 1 over sine, as we could, see right here. And if we're talking about specific sides, how are we getting, the hypotenuse over opposite here? Well, again, we were deriving it from just flipping this on its head, right? Flipping the first opposite over hypotenuse. But in reality, what's actually going on is we have sine, which again, sine of A is opposite over hypotenuse, right? So we just figured that out. It's opposite over hypotenuse. But sine of A is in reality, again, 1 over the cosecant of A, right? So 1 over cosecant of A, as we just described, well, this is hypotenuse over opposite. So this really becomes 1 over hypotenuse over opposite. And when you use keep, change, flip here, again, this is a complex fraction, you get what we originally started with, which is opposite over hypotenuse. And you can do the exact same thing to derive what cosecant is. So these should be equivalent statements once again. To derive what cosecant is, cosecant of A, we already established should be hypotenuse over opposite. But if we're talking about this definition where it's 1 over sine, then this should realistically be 1 over sine of A. And we knew what sine of A is, right? Sine is the opposite over hypotenuse, SOHCAHTOA, remember, SOH. So this is realistically 1 over opposite over hypotenuse. So this. And because we can, evaluate complex fractions, again, you could use keep, change, flip here. Eventually, what you just end up with is h over o, or hypotenuse over opposite, which is exactly what we figured out, right, for cosecant. So the relationships are the exact same thing. I'm not going to go through them, but it's the exact same idea for cosine and secant. So once again, just writing it underneath. That is entirely the same, and secant is the same thing as 1 over cosine. Okay, so again, they are just reciprocals of each other. This is really that's just what this all boils down to. They are purely reciprocals of each other. Whatever value you have for one of them, it's 1 over that value for its partner. So if you had, for example, sine came out to be 2, then cosecant is 1 over 2. And so on and so forth. Okay? So hopefully, I know that we just talked through quite a bit here. Hopefully it didn't mess you up too much. But as long as you can just remember the first 3, as long as you can just remember sine, cosine, and tangent, you can in fact get all 6 of them. In fact, we'll see in a second that as long as you just have one of them, you can really derive all 6 in total. But before we get to that, let's jump through some examples here. So I'm just going to go ahead and clear this off. Let's have an example where we have a triangle. It's going to be a right triangle, okay? And I know my drawing may not look like a right angle there, but it's a right angle as detailed by the box. We're going to call this angle right here theta. And we know the given information. We know that side right there is 5. We know that side right there is 4. We do not know this side. Currently, that side is unknown. What I want to do is, given this information, I want to find all 6 trig functions. Okay, all 6 trig functions. That means sine, cosine, tangent, cosecant, secant, and cotangent. Okay. All right, so let's get to work. Let's see how we do this. Well, first things first. Before we can figure out the trig functions, we need to figure out what this side is, right? Because right now we can kind of get a couple of them, right? We can get, sine, for example, sine of theta, we could figure out because we have the opposite, we have the hypotenuse, right? How do we know that 5 is the hypotenuse? Because 5 is the side that is opposite of the right angle, right? So we know 5 is our hypotenuse, and so we could figure out sine of theta, but can we figure out cosine of theta right now? Can we figure out secant of theta? No, right? We couldn't figure any of that stuff out. We'd also be stuck for tangent because we don't know what this is right now. So we should find out what x is. We should find our missing side. And how do we do that? Well, this is going way back, right? We know how to do this. This is Pythagorean theorem, right? Pythagorean theorem says if we have a right triangle, then we can find one of the sides just by plugging into the theorem, which is a squared plus b squared is equal to c squared. What is your c? C is always your hypotenuse. Always. Every time this is your hypotenuse. So to plug this in, we'll just leave one of these legs blank because we don't know what it is. We can even call it x. So we'll say, okay, x squared plus b squared. So we know one of the legs is 4. So we'll say x squared plus 4 squared is equal to 5 squared. Okay, simplifying this, we have x squared is equal to, and I'm just going to, in the same step, move over the 4 squared. So 5 squared is 25 minus 4 squared, which is the same thing as minus 16. And so we have x squared is equal to 9. And simplifying, we take the square root of both sides. We get x is equal to 3. Again, remember, guys, we do not need to put plus or minus here because we are solving for distance. We're solving for a length of something, right? Length, distance, measurement, that cannot be negative. So you don't need to worry about plus or minus 3. It's just positive 3 here. Okay, so great. We solved for x. X is equal to 3. So to redraw my picture here one more time. So drawing my picture, we now know that this is 5, this is 4, this is 3. That's my right angle, right? All right. So let's figure out, and of course, this is our theta here. It's very important to know which angle is the angle in question. Your sine and cosine, actually every single trigonometric function that you do is going to be thrown off if you choose this angle, for example, as opposed to choosing angle theta. So it does very much matter which one we're talking about. But again, we were discussing this angle, so we're going to keep it in that same corner. Okay, so let's figure out all 6 of the trig functions. Again, let's start with the 3 basic ones, sine, cosine, and tangent. So sine of theta, what should this be? Again, we know sine should be opposite over hypotenuse, right? So again, O over H. You don't necessarily need to write this if you could just remember it in your head, but I'm writing it just so we can all stay up to speed with this. So opposite over hypotenuse, what is this going to be? Well, the side that is opposite of my angle theta is 4. My hypotenuse is 5. So sine of theta should just be 4 over 5. Okay, let's move along. Cosine of theta. Cosine of theta should be adjacent over hypotenuse. So adjacent over hypotenuse means my side that is next to my angle, so in this case 3, over my hypotenuse, which is still 5. So we should have 3/5. And last but not least, for the first 3, we deal with tangent of theta. And tangent of theta should just be opposite over adjacent, right? O over adjacent. And what should this come out to be? Well, opposite is 4, adjacent is 3. So opposite over adjacent should just be 4/3 or 4 over 3. Okay, well, let's keep moving along. If we can figure out the first 3, we can definitely figure out the next 3. So the next 3 are cosecant of theta, secant of theta, and cotangent of theta, right? Well, these actually become really trivial. You don't even need to worry about remembering opposite over hypotenuse, adjacent over hypotenuse, or any of, that stuff. All you really have to remember, now that we solved for sine, cosine, and tangent, is that these 3 correlate to being the reciprocals of what we just found, right? So if cosecant is the reciprocal of sine, that just means that we're taking 4/5 and just flipping it on its head, right? So cosecant of theta should just be 5/4. And if, again, we're wondering where this is coming from, again, realize cosecant is the reciprocal of sine. So that means instead of it being opposite over hypotenuse, cosecant of theta should be hypotenuse over opposite, right? So our hypotenuse is 5. Our opposite is 4. So we should have 5 over 4. Okay, moving on, secant of theta, once more, we already solved for cosine, right? So since we already solved for cosine, just flip the fraction, flip it up. So instead of it being 3/5, it should now be 5/3. And last but not least, for cotangent of theta, instead of it being 4/3, it should now be 3/4. And that's all there is to it. And again, depending on what information you're given, you can find everything else, right? So we started this with only knowing that we have a right triangle and knowing 2 sides of that triangle. To be able to find the 6 trigonometric identities, we need to know all 3 sides of the triangle, right? So we need to figure out what x is. We figured that out using Pythagorean theorem, and so we figured that missing side out to be 3. Once we now know all 3 sides of the triangle, we can just apply what we just learned, right? SOHCAHTOA. And applying SOHCAHTOA, we found the following fractions: 4/5, 3/5, and 4/3. And then applying what we learned as well as far as the other 3 trigonometric functions being reciprocals, we can just take those fractions that we just gathered and flip them around. So instead of them being 4/5, it's 5/4. Instead of it being 3/5, it's 5/3. Instead of it being 4/3, it's 3/4. Again, the hardest part here is remembering the partnership between the 2, right? So remembering that tan goes to cotangent, remembering that cosine goes to secant, and remembering that sine and cosecant have the partnership here. If you mess things up, right? Notice how now how easy it is to mess things up, right? If you thought, for example, and I'm just going to leave the underlines here just so we know what's correct. If you thought mistakenly that sine and secant shared a partnership, then your answer to secant would be incorrect, right? You would think that, oh, well, secant is just the flipped version of sine, and so that would be, again, incorrectly 5/4. but that's not the case, right? That's cosecant. Cosecant applies directly with sine. Secant goes with cosine. And that's all there is to it. And cotangent, again, cotangent, tan, those go hand in hand. Okay, so with that being said, what I want you guys to do is try your hand at the first classwork assignment. So the first classwork assignment is same thing. I want you to find all 6 trigonometric functions based on the triangle with legs 3 and 6. So I'm going to draw the triangle here. Again, legs 3 and 6, and this is a right triangle. So find all 6 of the trig functions based on this information and see what you can come up with. All right, so first thing that we have to do, we have to figure out what this side is. If we don't know what that side is, we can't figure out like about 2/3 of the trigonometric functions. So, all right, let's find what that missing side is. To do that, again, we have to use Pythagorean theorem, right? So a squared plus b squared, is equal to c squared. What is c? C, in this case, is our missing side, right? C is always your hypotenuse. You know it's your hypotenuse because it's opposite the right angle, right? So we're just going to say, okay, well, then that would make this 3 squared plus 6 squared is equal to c squared. We'll just leave it as c squared. We don't know what that side is, so sure, that's our missing side. 3 squared is 9 plus 6 squared, which is 36, and this is equal to c squared. How do I handle this now? Well, again, it's c squared, so to solve for c, I need to take the square root, right? 9 plus 36 is 45, and, sorry, let me just fix that, 45. And to find c squared, you take the square root of both sides, just like we discussed. That's going to cancel out, and we are left with c being equal to square root of 45, but we can actually simplify that down, right? The way that we simplify this is we look for a square root that is a factor of, we look for a perfect square that is a factor of 45, and we throw it into its own square root, right? So in this case, we can break square root of 45 up into square root of 9 and square root of 5. And so when we simplify this down, this is the same thing as 3 square root of 5. Okay, great. So now we found c. c is 3 times square root of 5. Okay, fantastic. So we have our missing side now. All right, so to continue, what we have to do is we have to first, find, it's generally easiest to find the 3 standard ones. And then once you find the 3 initial trig functions, you can essentially just flip the fractions, right? And then you can find the other 3. So let's try to find, and I totally just realized I did not give you guys the angle. The angle should be right here. Angle theta, the angle that's opposite of the least side 3. I'll clarify that in the classwork assignment when it goes up, but if you're watching the lecture without having the classwork assignment open, my bad. The angle that we're discussing is the angle that is opposite the smallest side. Okay, so now that we have that sorted out, let's go ahead and figure out sine of theta, cosine of theta, and tangent of theta. So sine of theta, cosine of theta, and tangent of theta. To figure this out, remember, sine of theta is opposite over hypotenuse, right? So opposite is 3, and hypotenuse is, well, 3 square root of 5. We can simplify this, right? We have a 3 up top, we have a multiple of 3 in the bottom, so this simplifies to be 1 over square root of 5. And in general, when we're dealing with trigonometric functions, we like to rationalize the denominators. We like to make the denominators just a number, and if there is some sort of root, we generally tend to put that to the top. So just a quick refresher on how to rationalize. Remember that if we have a square root in the bottom, to rationalize, we multiply top and bottom by that same root, so square root of 5. Because what happens? We get square root of 5 squared in the denominator, which just leaves us with 5. And now we have square root of 5 up top. So we've now gone ahead and we've rationalized this. We get square root of 5 over 5, and that's our answer for sine of theta. Okay, so to continue, cosine of theta, well, cosine is going to be adjacent over hypotenuse, so that should be 6 over 3 square root of 5. So we have 6 over 3 square root of 5. And when we simplify this, again, we have a multiple of 3 up top, technically, right? 6 is 3 times 2. And we have a multiple of 3 in the bottom. So when we simplify this, we get 2 over square root of 5, and we do the same thing, right? To rationalize, so I'm going to just omit that rationalization step. Hopefully you guys remember how to do that. So we get 2 square root of 5 over 5. Okay? And last but not least here for tangent, well, tangent is opposite over adjacent, right? So this should be 3 over 6. So we get 3 over 6, and we know we can simplify that down, and that's just 1/2. So great, we found the initial 3, right? The initial 3 as follows: sine of theta is square root of 5 over 5, cosine of theta is 2 square root of 5 over 5, and tangent of theta is 1 over 2, or 1/2. So to find the next 3, cosecant of theta, secant of theta, and cotangent of theta, we can just take what we already know and just flip them, right? So cosecant of theta, remember cosecant applies, it shares that partnership with sine, right? So we're looking at sine here. We know we had square root of 5 over 5. So before you even try flipping this one, because again, you know that we're going to rationalize this, right? If you just take that, it would be 5 over square root of 5, right? And again, we know that we'd be trying to flip this in some way, shape, or form because we'd be trying to rationalize this. But instead of doing that, why don't we just take what we originally solved for? We found it to be 1 over square root of 5, right? So 1 over square root of 5, when we flip that, that's just square root of 5 over 1, which is just square root of 5. So great, we found cosecant of theta. And if you did it the longer way, where you took this and you flipped it, again, just to show you that it will work regardless. So we would be starting with 5 over square root of 5 because we take this fraction and we flipped it on its head. So to show you that it works, remember what we're doing. We multiply by square root of 5 over square root of 5. What this gives you is 5 square root of 5 up top, and this should give you a 5 on the bottom, right? And then you realize, oh, we have a 5 on the top and the bottom. That crosses out, and we're just left with square root of 5 anyway. So regardless how you do it, you should just end up with square root of 5 for cosecant of theta. Okay, moving on to secant theta. So for secant of theta, again, what we have to do is we look at cosine. We see that we have essentially this piece right here, right? I'm just going to skip the rationalization step because I can realize that when I flip this, my radical is going to be on the top, right? So we're going to be looking at square root of 5 over 2. And for cotangent, instead of it being 1/2, it's 2 over 1, and 2 over 1 is simply 2. Okay, so again, based off of everything that we just found, we can find the other 3, and now we found all 6 trigonometric functions. All right, so with all that being said, let's move on to a couple harder problems. So now this time what we're going to do is I'm going to give you guys essentially one trigonometric function. Our known value is going to be only one of them. And with that one, we're actually going to be able to deduce all of the other 5. Okay, so let's start with this. Let's say given theta is an angle of a right triangle. So I'll write it all out. Given theta is an angle of a right, and I'm just going to abbreviate, a right triangle with cosine of theta equaling 1/3. So again, notice how I'm giving you one of the trigonometric functions. We've already found this one. This is our given information, right? So cosine of theta is equal to 1/3. Let's find the other 5. So find the other 5 trig functions. Okay, so, and also what I want you to do is make sure that you're rationalizing the denominators here. Okay, so how do we go about doing this? Well, first, let's go ahead and just draw a triangle, right? It's good to keep track of what we actually have. So draw a triangle, make sure it's a right triangle. That one came out looking a little derpy. Let's try again. There we go. That's better. Okay, so what do we know here? Let's pick one. It doesn't matter here which angle you necessarily pick, because regardless what angle you pick to start with, you're going to orchestrate your triangle to be based off of that angle. So just for simplicity's sake, I'm going to choose this angle right down here, and this is going to be my angle theta. Okay, if, however, you chose the higher angle, so this one over here, this is not incorrect. This is totally fine to do. It's just that your triangle is going to look a little bit different than mine because your sides are essentially going to be flipped. Your hypotenuse is going to be the same, but this side and this side are going to be the exact opposite of mine. And that's totally okay. Okay. So with that being said, again, I'm choosing this to be my lower angle down here. And what do we know? We know that the cosine of theta is 1/3. So what this tells me, so cosine of theta is equal to 1/3. And what do we know about cosine? Cosine is equal to adjacent over hypotenuse, right? So we actually know the values of the sides of this triangle. Cosine of theta being equal to 1/3 tells me that my adjacent side of the angle is 1. So I have a 1 down here, and my hypotenuse is 3. Okay, well, if that's the case, we now have enough information to be able to find this missing side. So let's go ahead and find this missing side now. Again, Pythagorean theorem, right? So a squared plus b squared is equal to c squared. We know the hypotenuse, so we know what c is, right? The hypotenuse is always opposite the right angle. So we can say, all right, well, we have 1 squared plus b squared. I don't know what one of the legs is, so I'm just leaving that blank. That's still b squared, is equal to 3 squared. Okay, so this now, when I simplify this, I have b squared is equal to 9 minus 1. I just moved over that 1 squared, and 1 squared is just 1. And so we have b squared is equal to 8. And when we simplify this, we take the square root of both sides. We have b is equal to the square root of 8. And remember that we can break this up into square root of 4 and square root times square root of 2. And that simplifies to be 2 radical 2. So great, we just found the missing side here. The missing side is 2 square root of 2. And now that we found that missing side, we can find the other 5 trigonometric identities, right? I'm just clearing this just to make some space for myself. So let's go ahead and start with sine and tangent. And it's easy enough. We can already do secant because we were given cosine. But let's go ahead and start with sine and tangent nonetheless. So to do sine of theta, it's opposite over hypotenuse, right? So opposite is going to be the side that is opposite our angle theta. So that's going to be 2 square root of 2, and our hypotenuse is 3. So sine of theta is 2 square root of 2 over 3. Perfect. We're done with sine. Let's move on to tangent. So for tangent, we have, again, should be opposite over adjacent. So it should be 2 square root of 2 over 1, which is just 2 square root of 2. And last but not least here, if we're doing, well, not last, but we did cosine, right? So the one that jumps out at us, the one that it's the partner of cosine, the reciprocal of cosine, is secant. So for secant here, instead of it being 1/3, it should just be 3 over 1, right? So instead of it being 1/3, we flip it over, and 3 over 1 simplifies to just be 3. So secant of theta is just 3. And to verify this, again, what is the reciprocal of cosine? Well, cosine is adjacent over hypotenuse. So the reciprocal of that should be hypotenuse over adjacent. And what is hypotenuse? Hypotenuse is 3, adjacent is 1. So you would have 3 over 1. And that's exactly what we got here, right? So it simplifies to be 3. To find the other two, well, we solved for sine and we solved for tan, right? So let's figure those out. So cosecant of theta is the sine of theta, but just flipped. So it should be 3 over 2 square root of 2. Remember, we do like to go ahead and rationalize things. So I'm going to multiply both top and bottom by square root of 2. When I do that, I'm going to get 3 square root of 2 up top. And then I'm going to get the first 2. That's still there, right? So that 2 stays there. And then square root of 2 times square root of 2 is square root of 2 squared. So that's 2 times 2 in the bottom now. And 2 times 2 gives me 4. So when I rationalize this, I have 3 times square root of 2 over 4. Okay? So we're done with cosecant. And the last one that we have to do is cotangent of theta. And cotangent of theta, again, should just be the reciprocal of this piece. So instead of 2 square root of 2 over 1, should be 1 over 2 square root of 2. And one more time to rationalize and just to show the step, multiplying both top and bottom by square root of 2. And this should give me square root of 2 on the top and then square root of 2 times square root of 2 is 2. And we already had that first 2 down there. So 2 times 2, which also gives me 4. So cotangent of theta is square root of 2 over 4. So we were able to determine all 5 of the other trigonometric functions here, sine, tan, secant, cosecant, and cotangent, just from having the information of one of them, so one of the trig functions, and also the knowledge that this is a right triangle. So that's all you need. If you know that it's a right triangle, and if you're given one of the trig functions, you can find the other trig functions as well. Okay, so what I want to do now is I just want to put you off to your last classwork assignment for tonight. So the last classwork assignment is the same exact question. So again, I want you to find the missing 5 trig functions, but this time the piece that I'm giving you is I want you to do that with the given that cosecant of theta is equal to 7 over 4. Okay, so that's your given statement. Try to work things out and see how far you get. All right, so let's go ahead and get started with this. First things first, again, I strongly recommend drawing a triangle so that way you can, keep track of everything, right? So we know it's a right triangle. Again, it's the exact same conditions. Theta is an angle of a right triangle, and we're just given this piece of information about cosecant. So I'm going to pick, again, this piece down here to be theta. And let's go ahead and get started. So what is cosecant of theta? Cosecant relates to sine, right? That's its partner. So if cosecant of theta is 7 over 4, we can already figure one of the trig functions out. We should know then that sine of theta is just the reciprocal of 7 over 4, which should just be 4 over 7. And what do we know about sine? Well, we know that sine is opposite over hypotenuse, right? So we know that this, and again, just to write it, opposite over hypotenuse, and obviously this one was hypotenuse over opposite, and it doesn't matter in what order you do. You can either write, the numbers on your triangle first, or you can find the correlating trig function that matches, the partner that you were given. Either way, we should get the same thing, that your hypotenuse is 7. So again, notice I'm putting 7 here because it's opposite of the right angle, and the leg that is opposite of your theta is going to be 4. So I'm going to put 4 right there. So with that being said, let's go ahead and find this missing leg here. So to find the missing leg, we have a squared plus b squared is equal to c squared, right? Okay, so to get things going, we know the hypotenuse, we know what c is, so this is 7 squared. We know one of the legs, so I'm going to write this as 4 squared, and we're missing one of those legs, so still just a squared, right? We're solving for a. Okay, so to solve for a, we move things over, so we have a squared is equal to 7 squared is 49, and moving over the 4 squared, I'm just going to go ahead and subtract off 16, right? 4 squared is 16, and I'm subtracting it from both sides, so we have a squared is equal to 49 minus 16. Okay, so simplifying again, we have a squared is equal to 33. And when we take the square root of both sides, we are left with these canceling out. So it's just a is equal to square root of 33. We can't actually do anything with 33. 33 is not a prime number, right? 3 goes into it and 11 goes into it, but neither of those are perfect squares. So even if we split it up into square root of 3 and square root of 11, it's not going to help us simplify. So we're just going to leave it as square root of 33. So we come back to our picture here, our little diagram, and great. We know now that this is square root of 33. Okay. I'm just going to clear this off to make some room for myself. So we already figured out, we were given 1. We already figured out 1 based off of the relationship that it has with its reciprocal trig function. So we know cosecant and we know sine. Let's go ahead and find cosine and tangent next. So cosine of theta. What should this be? Well, this should be this should be adjacent over hypotenuse, right? Cosine is adjacent over hypotenuse, so this should be square root of 33 over 7. The side that is adjacent to your angle or next to your angle over the hypotenuse. Okay, and for tangent of theta, well, this should be opposite over adjacent, so 4 over square root of 33. And for square root of 33, again, we do like to rationalize. So what do? We multiply top and bottom by square root of 33, and that should give us 4 square root of 33 over 33. Okay, so we have now found 4 in total, right? We have cosecant, sine, cosine, and tangent. Let's find the last 2. So finding the last 2, that's going to be secant and cotangent. So secant of theta and cotangent of theta. And secant of theta relates to cosine, right? So we can just take what we found for cosine and flip it. So this is 7 over square root of 33. And once again, because we're rationalizing, 7 times square root of 33 over 33 should be your final answer for secant. And for cotangent, well, again, we know that tangent originally was this before we rationalized, right? So I'm going to use that instead of using this piece, because if I use that piece, I can get the same answer anyway, but it's just more work, right? When I take this, which is what I originally found, I know that when I flip it, the radical is going to be on top. So we know that we should eventually end up with square root of 33 over 4, and that is our final answer for cotangent. So we ended up with all 6 trig functions, just starting with the given that cosecant of theta was equal to 7/4, and that theta was an angle part of a right triangle. Okay, so that's where I'm going to go ahead and end this lecture. This is enough for tonight. We'll probably finish up trig functions in the next lecture, and I believe, don't quote me, but I believe that'll be it for trigonometry. Okay, so in any event, enjoy the rest of your night, day, morning, whenever you're watching this, and I will talk to you next time. Enjoy. Have a good one.